Welcome to this critical systems presentation where I'm going to be discussing about the prototyping of an authentication and an authorization platform used for financial systems. So first we're gonna define the problem statement um, associated with developing financial applications, and we'll do this by defining what are critical systems, the components of secure and reliable systems, the importance of authorization and authentication flows to data security, um, how to perform threat and risk analysis, and the required ethical compliance for a system to transfer data securely. So critical systems are programs which may compromise the safety of its users and the software stakeholders in case of operational failure. So the safety impacts could include health hazards, sensitive data leakage, and financial or organizational disruptions. And the system failure can be caused by dysfunction or at the hands of an attacker. And there is some examples there which show the impact um, critical systems have had uh, on organizations in the past when they have resulted in system failure. So when developing secure financial systems, we have to address the fact that attackers may exploit the vulnerabilities of an application uh, to expose, modify, or block the stored data and compromise its safety. And secure systems take measures to maintain the CIA security components, protecting the user's confidentiality, integrity, and availability, ensuring that only authorized parties have access to the data does not become corrupted or tampered with, and the service can be accessed when necessary. And evaluating system reliability can be done uh, with risk analysis techniques and software testing procedures. And we define reliability as the measure of a program's operata operability without functional or malicious failure in a defined environment. And authentication and authorization flows are the standardized methods for allowing user access to the system, and they securely process user-defined credentials to identify the user and present authorization policies to allow restricted access to the system. So when developing those systems, we must protect the data transmission to ensure the auth system cannot be exploited with an attack. And these systems are developed to reduce the probability and intensity of the possible damage resulting from infringement of the CIA security principles. The prototype developed as part of this report is developed with the help of a cloud computing service, Amazon AWS, to establish a demand scalable server infrastructure. So what is cloud computing? These are services which distribute computing resources, offering on-demand scalable data processing without the need for physical hardware. And cloud computing services use infrastructure as code, which allows the infrastructure to be provisioned and managed through configuration files, streamlining the process of infrastructure management and providing common software architectural patterns. So why should it be used for financial system security? Well, it's less susceptible to availability issues as the resources are distributed globally and um, provided to uh, process the requests on demand, um, which prevents any downtime due to physical breakdowns or request throttling. Um, and why it's also used is because on-premises infrastructures require high-level security responsibilities, which are addressed in the services offered by AWS, and this has been proven by a survey which has found that 41% of enterprise workloads currently run on cloud distributed platforms, and they are predicted to suffer at least 60% fewer security incidents. So when developing secure systems, we should analyze the common threats to pinpoint the vulnerable system areas and highlight the methods for risk mitigation and control. So in this report, we have identified the following types of threats. So we have brute force exploits, which continuously try out combinations of characters to crack the user password, API encryption keys, um, data transmission encryption keys, or the server access credentials. And these could be controlled using multi-stage authorization flows, um, such as multi-factor authorization, which issues tokens to the user's device or email, or CAPTCHA puzzles to limit the number of attempts coming from the same origin. Denial of service attacks are attacks on the service availability, attempting to overload a target with large volumes of requests, and this can degrade or completely block access to a system. In cloud computing, this can also incur large costs in computing resources. And mitigation of DOS attacks involves locating the targeted components using monitoring features, uh, con confirming the presence of network overload uh, using request interpretation. Uh, and we can also use load balancing techniques to throttle the and limit the um, processing of DOS requests uh, and reducing the damage on the service availability. Identity-driven attacks target user credentials to gain unauthorized access by impersonating their identity. So these could include man-in-the-middle attacks, which eavesdrop on the client-server communication, intercept the transmitted data, uh, typically exploiting a user's unprotected network or malware in their system. Uh, and some examples of man-in-the-middle attacks include session hijacking, which copies the token associated with a user login session, and the damage can be minimized with multi-factor authorization to allow the real user to confirm the login, uh, or fraud detection methods, which can monitor account usage and flag anomalies and then challenge them. So when we develop with cloud computing, misconfiguration of the used services is responsible for 90% of all cloud security breaches. Um, so we should use strong access management protocols and employ the principle of least privilege to allow only the relevant functionality for a given user, request, or operation, which limits the possible damages stemming from unvalidated requests. And this is because APIs used for communicating with the cloud services may expose severe vulnerabilities if they are inadequately secured. So I used the common vulnerability scoring system to calculate the level of danger and operational risk emerging from the identified threats by examining their attack area, the assets at risk, and any existing countermeasures. And in turn, this forms a specification for the critical system to follow in order to achieve the minimum security requirements. So here is the vulnerability scoring calculations for the previously identified threats. And here we can see that denial of service attacks would present the highest risk rating based on the vulnerability score, followed by brute force exploits, unauthorized API access, uh, user permissions exploit, and man-in-the-middle attacks. So controlling this inherent threat requires the developer to balance the CIA triad to maintain data confidentiality, integrity, and availability. And confidentiality can be maintained using encrypted connections, protected key storage, and principle of least privilege defined authorization protocols, uh, restricting the access to the API and protecting the user data from all identified threats. Uh, Maintaining integrity can be achieved by designing an effective threat control and response procedure to prevent data changes due to attacks or system faults. This can include functional validation, rigorous backup processes, and monitoring techniques. And keeping the data secure and up to date may, however, affect its availability through time-consuming operations such as multi-factor authorization, complex data transfers, or temporary shutdown of a service as part of a threat response. However, an effective threat control and response procedure will keep the data as secure as possible without major drawbacks to the user experience. And developers should also consider the ethics required for development of critical systems, as meeting compliance standards presents that a company takes the necessary steps to safeguard their customers' data, minimizing the risk of legal penalties or a loss of customer assets. Um, so we have the General Data Protection Regulation, which is the set of provisions to protect digital information of EU citizens. Um, and the GDPR states that data collected from the public must be processed lawfully and in a transparent manner, deems it mandatory for the data processor to implement appropriate measures to ensure data security. Uh, they want us to implement regular testing and monitoring procedures to evaluate and ensure the resilience of the processing system. And failure to comply with the GDPR in a way that violates data processing principles or the data subject's rights could result in fines of up to 10 million euros, in addition to being liable for the compensation of any persons who have suffered damage as a result of the infringement. We also have the PCI DSS, Payment Card Industry Data Security Standard, which is a set of guidelines for maintaining the security of financial data transmissions. So those guidelines want us to identify and address all known system vulnerabilities. They want us to define the flow of network transmission and document any mechanisms for risk mitigation, which provides the proof of PCI DSS compliance and presents material needed for further re-evaluation of the system vulnerabilities. Finally, we should control and monitor the traffic from publicly available components using a robust procedure which responds to suspicious activity detections. We also have the Web Content Accessibility Guidelines, which ensure that an application meets the needs of all users, inclusive of individuals with disabilities and limited technical expertise. And those principles ensure that interfaces are perceivable, operable, understandable, and robust, basically allowing for interactions and easy interpretation of the application functionality. So to summarize the problem, critical system development concerns managing many risks which concern the users and the organization's safety. And we have examined a range of threats present in financial system development and identified the control mechanisms for their mitigation. And those included authentication and authorization protocols, multi-factor authorization and fraud detection, and monitoring and blocking capabilities to detect and respond to attacks. And secure data transmissions are required for legal compliance with the GDPR, posing a risk of legal repercussions if those are not followed. And by employing the above mitigation methods and documenting the system design, the prototype aims to follow the PCI DSS guidelines to classify as a secure financial application which maintains user data confidentiality, integrity, and availability. So in the next section, we will be discussing the system design of our secure overflow prototype, where we organize the program structure in a manner that ensures scalability, modularity, and maintainability, um, following clean coding principles to ensure the program remains structured, facilitating future enhancements, and also design and assess the security of data communications between the front-end desktop application and the AWS computing resources. So solid programming principles are recommendations for reducing the component dependencies, allowing teams to work on components independently and making the components easier to test and debug. Um, so the SOLID acronym stands for 5 key principles: the single responsibility principle, where each module should only have one responsibility; the open closed principle, where functions should be open for extension but closed for modification; the list code substitution principle, which guides us to use polymorphism to create subtypes of a class, and making sure that the parent classes are replaceable with their subclasses without affecting program correctness. Uh, the interface segregation principles, which guides for the use of interfaces, um, so that components are not forced to depend on functionality which they do not use. Um, those interfaces should be designed only to specific needs. And we also have the dependency inversion principle, which uses abstraction so that high-level modules are not dependent on low-level modules, which promotes looser component coupling. So our front-end application is handled using a desktop WPF utilizing C# in the .NET development platform. And the front-end application is used to generate the user requests and handle the cloud service communication. And it's gonna do that using libraries such as the AWS.NET SDK. And our architecture is composed of controller singleton objects, which act on and define the data of model objects. So the controller objects are the authenticator and view controller, for example. And the model objects would be sessions, session clients, and users. And the authenticator creates the session client upon successful authentication, which opens the API connection using the session object containing the user access tokens. And the view of the application is then updated based on the data retrieved from cloud data stores. And then here we have the backend microservice architecture. So when the user interacts with the app will first connect to Amazon Cognito, which handles the authentication flow of the application, encrypts the login credentials, stores them in the cloud, and in response to correct uh, credential validation, it returns a token containing the user identity and their access levels. And multi-factor authorization is also a built-in feature to Amazon Cognito. Um, so then the access level is defined using AWS Identity and Access Management, IAM, which handles the configuration of permission policies to be attached to other services or users, and those determine the access level that resource has to other services. So once we have the access token, the app then connects to API Gateway, which manages API deployment. Um, and it's used to securely communicate with authenticated requests from the front end. And a RESTful API pattern is employed, which restricts the functionality of the API to predefined methods encoded using get, post, put, or delete requests, which promotes a modular request definition as the services which send those service uh, requests do not need to know the internal workings of where the request is going or where the request came from. Any traffic which passes through the API gateway will be monitored using the CloudWatch, CloudTrail, and X-Ray services, uh, monitoring the health and efficiency of the application and collecting data about latency or any errors in the traffic. And the API gateway will also be protected using AWS, WAF, and Shield, uh, which protect the gateway from some common attack patterns. Um, and API requests will invoke some Lambda serverless functions, which are scalable methods for processing requests which run compute tasks on remote machines, and we'll use them to perform operations such as fraud detection or data retrieval from our DynamoDB data stores. And DynamoDB is a non-SQL database which attaches a set of data to a specific index key, and by setting the index key to a Cognito-generated user ID, we can restrict the requests to retrieve data only specific to the originating user. Our application prototype follows a sequence of validating request input data, communicating the credential data to Cognito, sending an email verification token to the user's email, communicating the verification token in exchange for the session token containing the user access data and their identity, authorizing an API connection with the use of the retrieved access token. Then we'll issue a request to the API to retrieve the account details and also log the request to CloudWatch. We will check the operation against the defined IAM policies. Then we will validate the request using a fraud detection function, comparing it to an account's historical data, such as the user's geolocation or device. And after the request is validated, we will invoke a function to process the request by either retrieving or storing some account data. And then we will return the relevant information to the via the API connection, which will be sent back as a response to the front-end application and presented in the user interface. Next, we will demonstrate the prototype workings. So, we have our screen here, and we can register for an account. Just to show some input validation, we're gonna try making up an invalid inputting some invalid credentials. Which, as you can see, throws some validation errors. Next, let us just create an actual account. So we will enter our credentials. And as you can see, we get a message that our account was successfully created, and we can check our email for the verification code. So when developing the email distribution, we have used a sandbox mode, which means that only specified email addresses are allowed to receive the email messages, because setting up a public sending domain requires setting up the domain and also receiving some permissions from AWS. So we had to be restricted to only using specified email addresses, which means if you download the application, you probably won't be able to test its functionality. But here is the code we received in the email. So we're gonna verify our email, and as you can see, the user was verified successfully. And we're gonna now try logging in. I'll enter some invalid credentials here. Sign in failed because of incorrect username or password. So now let's try the correct credentials. And access to the account requires a multi-factor authorization token. So this one should also arrive in my email. There it is. Once we pass that in, the data from the um, server will be retrieved and presented to the UI. So as a test method, I have invoked a function which whenever a user is created, they get assigned a random account balance. Um, so we can either sign out, or if we even close the application and reopen it again, and if we log in, and the session will persist and we will not require an MFA token. However, if we click sign out, and the multi-factor authorization token will be required again. Uh, now, we can view the request in our AWS console. So CloudWatch has logged the request to the API Gateway execution logs, which shows us that we have successfully completed authorizer execution, sent a put method on the get user balance API resource, which invokes a lambda function, which then uh, responds with status OK and latency of 360 milliseconds. So CloudWatch allows us to aggregate the log data and uh, produce some graphs which display, for example, here we have some spikes in latency, which is when I was running my denial of service tests. And we can also configure this monitoring service to send alerts in case thresholds are exceeded. So next I'm gonna show you the REST API developed for the prototype. So we have this API here, and we have the get user balance method on it. And we also use our Cognito as the authorization method for the API. So here is our Cognito user pool. So we'll enter this one and view our users. So here is my email address. When I click on that, and here is some of the data attached to AWS. We have our unique user ID here. And what Cognito also does is we also have a pre-authentication and post-authentication Lambda triggers, which are our fraud detection methods. And what these do is pre-authentication basically checks any recent failed attempts and logs the um, blocks the access to the account if it exceeds a limit. And our post authentication Lambda trigger basically sends the user a message when their account was used from a new location. So we can see this email here. Your account was just accessed from a new IP address, 8623. If this wasn't you, please secure your account immediately. So when we send the API request to get the user balance, it's gonna invoke a Lambda method, which retrieves data based on the passed in based based on the accessing account ID, and it's gonna get it from DynamoDB user data, which contains the account balance. Which we also have the trusted devices table, which contains our IP address, which we use to access the account. We have device and account usage, which logs the failed attempts to the account and failed attempts coming from an IP address. And we also have a method which monitors any modifications on user data. So if we try to edit the balance here, so they make that 900,0,0, save that, and CloudWatch logs should, after refresh, show us the old balance and the new balance. Yes. You can see event name was modify, and it shows us the old image, new image. Our user data also has backup defined on it, which can be found here. And these basically are run after every change made to the database and allow us to restore any modified data. So next, I'm just gonna show you some of the tests developed as part of the application. So we have developed some unit tests to check the workings of the authentication system, such as how it behaves under correct credentials, how it behaves under incorrect credentials, or when we try to access a forbidden resource, the method should fail. We also have the JWT token tampering test, which checks whether an expired JWT will be rejected or whether a tampered JWT will be rejected. And tampering is basically attempting to change the payload to exploit, for example, change the configuration of the user permissions, for example, which could be used to exploit access to the system. We also have a brute force simulation, which I have commented out here, because running it will block access to my to the test account, and this basically ensures that the access is denied. And we also have a method to simulate an authenticated DOS attack. So basically, we log in with authorized credentials, and then we send many requests to the API to find out how the system behaves. So first, let us run our unit tests. So tests, run all tests. We should see all of these succeed. Something didn't get built. 1 second. Here we go. Okay, the tests were completed successfully, giving us this check mark, and except the brute force simulation, which was commented out. And we will now also show the authenticated DOS attack. So to do that, we click on this project and we will debug, start new instance. Excuse me, I had a syntax error there because I was pressing some keys. Let me run that again. Debug, start new instance. And this is gonna require a verification code from my test account email. We will pass that in, and then 50 requests will be sent out. And because there is rate throttling or rate usage implemented in AWS, some of the requests return internal server errors, which shows us that there is some form of DOS attack protection. Finally, we will just uncomment this code here and run our tests again. And this should show us that the access to the test account was blocked, basically. There we go, test completed. The response was rejected successfully. So now if we try to log into the test account via the application, we get a message saying that pre-authentication failed with error, too many failed attempts exception. So next we'll evaluate and reflect on this project by discussing the developed skills, examining the validation results, evaluating the reliability and security of the prototype, as well as its capabilities for future improvement, stating how the prototype complies with ethical standards, and determining the path for further development. So taking upon this project has yielded invaluable skills associated with designing secure, reliable systems. So threat and vulnerability analysis procedures. So these skills include threat and vulnerability analysis procedures, the definition of potential risk severity using vulnerability scoring, the development procedure of authentication and authorization flows, and using cloud technology to establish secure server communications. Have gained skills related to the knowledge of the ethical statements regarding secure data processing. We have gained system design skills, employing the use of solid principles to provide system modularity. And we have also learned about the testing and validation techniques, describing system efficiency, reliability, and security. So performing unit tests on the authenticated procedure functionality has demonstrated operational success under the provided test cases. Um, the log data has presented that most requests are handled successfully, provided they have been appropriately validated. They are processed in under 500 milliseconds, which offers fast data availability. The penetration tests have shown reliable, reliable protection in response to a simulated attack pattern, and the application successfully deters brute force attempts, throttles the processing of repeated requests attempting to stop DOS attacks, and data confidentiality is maintained thanks to the developed authentication and authorization flow, which prevents access from unknown sources and protects from permission exploitation by validating the token integrity and restricting authenticated access only to relevant methods. And code injections are not possible thanks to the limited API communication provided by the RESTful API architecture. So the program's adherence to solid principles, our backend microservice architecture allows for a scalable modular configuration which can be easily extended with new or improved functionality. However, the front-end application could have utilized interface definitions for our controller classes, which would allow for easier test integration and functionality extensions in future enhancements. Um, and although the prototype has yielded a reliable, secure system, the singleton pattern used for the controller classes resulted in couple code executions, which makes it more difficult to scale and maintain the code base. However, despite this, the polymorphism approach for defining the user and its subclasses has successfully abstracted the operations performed by the subclass, allowing for the implementation of different user types with varied operations in future developments. The application's ethical compliance. Uh, The system successfully follows the objectives outlined by guides for GDPR and PCI DSS compliance. So GDPR compliance is demonstrated by the system's capabilities for maintaining data integrity and confidentiality. We have a monitoring and attack detection functionality, which presents an ability for the software to stay accountable for protecting of its users' data. And a data backup procedure allows for the environment redeployment if the system becomes compromised, which keeps the data integrity intact. The PCI DSS standards have been addressed by integrating security protections against the identified threats. The process has been documented, which provides a means for further vulnerability assessments. And although a threat response plan has not been assembled, the prototype addresses the identified vulnerabilities to ensure only authorized users can access their data. And we also monitor the API access and send alerts when suspicious activity is detected. The VCAG compliance has been addressed by generating contextual information in response to any problems arisen in the communication process, which you saw, like any errors or misinputs that the user experiences. And this gracefully handles errors to ensure the application remains stable and functioning. And the understandability is maintained by labeling the present features, explaining the required processes, and helping the users input correct information. Further developments to VCAG could have been made to ensure the application is perceivable and operable using non-standard controllers by impaired users. And the path forward for um, secure system development includes further improvements to the architecture, such as refactoring using interface definitions to demonstrate the open-closed principle of feature extension, or restructuring the coupled components to maintain the single responsibility principle. We also need to re-evaluate system vulnerabilities, um, as the maintenance of system security requires constant reassessment of the vulnerable system areas. The, and an example of this is the current methodology for retrieving the API endpoint can expose the endpoint if an authenticated request is made to the endpoint distribution service directly. A better approach would be to issue per user API keys to fortify the secured connection. And the path forward is also to um, design a managed threat response. So after we detect the presence of a DOS resource utilization, the system should block access originating from the source. Additionally, a procedure should be designed to respond to data breaches appropriately, such as via redeployments of the environment after the attack is mitigated and the damage is repaired. So to conclude, developing secure financial systems requires the formulation of a problem statement addressing threat management and legal compliance. Identification of possible threats allows for the preparation of a threat mitigation strategy, and designing reliable systems benefits from solid principles to make the code base more maintainable and scalable for further improvement. And cloud technology can effectively aid with development of secure systems, providing built-in functionality for identity authentication and permission authorization. I hope this was all right. Thank you very much.